Hello everyone. So as mentioned, my name is Martin Sever and I come from company RLS. And I would like to show you a little bit about wafer level IC testing in our company. So RLS is short for rotary and linear sensors. We've been founded in 1989. We're located in Poslovna Zona Komenda, and currently we're employing 278 people. And we make encoders. We make magnetic, linear, and rotary sensors. They can be absolute or incremental type. We offer various industry standard communications, different installation types, selectable resolutions, and I'd also like to mention that we are really strong at custom solutions. Application-specific integrated circuits, or ASICs, are really important in RLS. They're a core of what we do. And why is that? Well, first of all, they offer us ability to implement some custom solutions which are not available otherwise. But in RLS, especially strong is a combination with chip-on-board technology. So technology of placing your chip directly on sorry. Does it work? Is this on the monitor? Okay. Hook up over time. Okay. So placing the die directly on PCB, then bonding this die and encapsulating it. And this combination then brings us ability to implement high density integration, achieve high processing speeds, improve signal to noise level, and also to achieve tight mechanical tolerances, both on PCB, but also in reference to our magnetic actuator. And ASICs also represent high added value for us. We get ASICs on wafer level, and we have our own chip-on-board technology in-house, so we can process the thing all the way down, which means that it's also quite cheap for us. Since we're also doing in-house testing, we also have quite good quality control. Currently, we're using 8 proprietary ASICs in RLS, and these were developed by external partners. But as of start of 2022, we have our own ASIC design team for all the future projects. And a part of this team also work on developing testing equipment and procedures for wafer level IC testing. So now let's go to testing and start with something really simple. In testing, your input would be untested silicon wafer, and the output would be a tested wafer with identified bad dies. And you can do this by physically inking your wafer, so actually putting a black dot on it, or you can accompany your wafer with electronic map, like you see here on the bottom. In RLS, a typical setup to achieve this would look something like this. So you have a wafer prober, which is your positioning system for wafers. You have a probe card that goes inside the wafer prober, which helps you contact individual die on the wafer. Test device, which performs electronic tests to determine if this die is okay. And a PC with some software, which makes the whole thing automated. So now I would like to go a little bit more into depth with these components. And I would start with a probe card. So probe card is basically a piece of PCB with some things attached to it. And since we're making magnetic encoders, we would like to have some magnetic field present when we're testing. And usually we do this by attaching either a coil or a rotating permanent magnet on the top of our probe card. On the bottom side, you would have some metallic needles or cantilevers. And with these, you probe directly into pads of the die. And this makes electrical connection, so you can test your die just as it would be in a coder, for example. Here you see an example of actual needles. In this case, it's around 50 needles on the left side. And on the right side, you have a part of a die that was already tested. What you can see here is 3 pads with some markings left by these needles. These pads are around 100 micrometers in this case, and as you can imagine, you need to have quite accurate positioning system to be able to align each individual die under your needles. And this is achieved by wafer prober. So this is basically a very precise positioning device which allows us to go from die to die on wafer and test it. Our prober has approximately plus minus 2 micrometer positioning accuracy. We can load up to 25 wafers, a whole batch in one go. 4 to 8 inch wafers are accepted. And it also serves as a temperature regulator, so we can test our device across the whole temperature range, and we can achieve temperatures from -40 to plus 150 degrees. And if needed, you can also do the inking, as I've shown before. The test devices are something that are connected to a probe card, so pieces of electronic equipment which perform some tests to determine if your die is suitable or not. We develop these in-house, typically around a microcontroller. Per each die, we usually perform from 10 to 1,000 tests, and typically this takes up to 3 seconds. We also perform calibrations of these devices and store the data inside, meaning that these are easily swappable. If something goes wrong, we can just swap them with little or no downtime. On the PC, we run our own testing software which connects the whole thing. It's developed again in-house. It controls both test device and the wafer prober, and it makes the whole thing automated. The outputs are some log files, test results. It's also integrated with traceability system, meaning that if you would have an encoder that doesn't pass the final test, or maybe even there's a problem at the customer side, you can always go back to results on the wafer level, and you can see if something was amiss already back there. We can combine multiple tests into one final map. For example, if you tested 2 different temperatures. And we can also do inline programming during the test or trimming of these dies. Or we can do this as an individual procedure. These test results are then fed into a database. And with this database, we can do some analysis. And we have developed, again, in-house our own software to do that, which is quite strong analytical tool. Just to show you what it can do, we've plotted here some data in 3 different ways. So this is one of those tests for one type of the die, all the data that we have, plotted in 3 different ways. So first, we've plotted these results by value, so we have a distribution, and these red dashed lines represent our criteria. So you can see that in this case we're quite well within our limits. On the second plot, the same data is plotted by time. And here, if you would see a large step in this running average, this would indicate that something significantly changed either in the wafer process or in testing process. And both of these should be a red flag for us, and we need to investigate what's going on. And the final map, here we plotted this data by position on wafer. So in some cases, if you see something like that, this is normally fine because the shades are kind of the same all over the wafer. But in some cases, you might see some edge defects or something else, which might indicate that your wafer processing might not be as good as it should be. So some final thoughts. In RLS, we do our own in-house IC testing, and we develop a bunch of stuff ourselves. Test devices, test software, and analysis software. Currently, we are testing around 300 wafers per year, and we have already tested about 3.5 million dies. So this is all from my side, so thank you for your attention.
Questions, please. I have a question.
Okay.
The tester you have
Yep.
is able to test analog and digital circuits and so on, or not?
The tester itself, are test devices or the prober?
I mean test devices, including the prober,
Yeah.
because with the probing it's difficult to test sensitive analog things.
It tests whatever we design it to test.
Okay.
Because, yeah, and we test both, yeah, analog and digital designs.
Okay, thank you very much.